One other little topic I wanted to get at is what we refer to as the special triangles. Um, and this is an alternative way that trigonometry was taught historically, and actually a lot of people will teach trigonometry this way in other countries. So this is just something I wanted to mention because I've seen students using these triangles, and they're kind of like an alternative way of memorizing the special angles other than the unit circle. Like in chapter 4, I taught you guys about, to use the unit circle and to memorize those special positions, pi over 6, pi over 5, pi over 4, pi over 3. We talked about why those positions have the angles that they do. But there's actually there's if you memorize two special triangles, you can actually remember all of those key angles from the unit circle very simply. And that's exactly what I wanted to show you guys. And maybe this method will resonate with some of you guys, and maybe not. But anyways, it's just an alternative way of memorizing 30, 45, and 60. But basically, if you remember these two triangles, imagine an isosceles triangle, and both being right triangles, where both the legs are length 1. This would be special triangle number 1, and the secondary special triangle is where one triangle has side length 1 and the hypotenuse is length 2. So basically, let's go ahead and look at how those triangles work and solve the remaining sides. But basically, if we memorize these basic triangles, all of trigonometry, those special angles come from these. And actually, notice that if this triangle was isosceles, there's a property of isosceles triangles where the two other angles must be equal. So if it's a right triangle, then those two angles, if they must be equal, they must both be 45 because they have to add up to 90 degrees, as I was talking about in the last video. But basically what this implies is that, say for example, I wanted to know the tangent of 45 degrees, and as we know that's equal to the tangent of pi over 4. Well, if I'm using SOHCAHTOA, which is how a lot of people memorize their trigonometry, I know that tangent is equal to opposite over adjacent, 1 over 1. I don't know if you can hear my dog, he's freaking out about something. But the tangent of 45 is equal to 1. And really, this is the same thing that I would conclude from the unit circle, right? If I took the tangent of pi over 4, well, that location has y of root 2 over 2, x of root 2 over 2, tangent is y over x, which would give me a ratio of 1. It's all consistent. But this is a way that a lot of people don't really understand the unit circle and how to solve trigonometry using it, and this is a different way they might figure it out. And a lot of people actually, have learned to solve trigonometry this way. The reason I don't like to teach this way first is there's no understanding of why. Like, we can memorize all this stuff, but we won't really get it. And the unit circle helps me to really understand how trigonometry really works. Anyways, and also to find the third component, let's say I want to know the cosine or the sine of 45 degrees. Well, the third side I could solve via Pythagorean theorem because a squared plus b squared is equal to c squared. So 1 plus 1 is 2. And c would be equal to the square root of a squared plus b squared, which is the square root of a squared plus b squared, which is 2. So anyways, the third side of this triangle must be rad 2. And so notice that what I could also figure out is, like, for example, I wanted to solve the cosine of pi over 4, which is equal to 45. Well, that's going to be adjacent over hypotenuse, 1 over rad 2, which if I rationalize that by multiplying top and bottom by root 2, that would give me root 2 over root 2 times root 2 is 4. But basically, notice, oops, I messed that up, root 2 over root 4, which is 2. But notice what I would get is that the cosine of pi over 4 is root 2 over 2. Again, I'm using SOHCAHTOA, but I'm getting the same answer that I got from the unit circle. And same with the sine. Since the opposite is also 1 and hypotenuse is root 2, I get the same thing. Anyways, I can generate all of those special angles, pi over 6, pi over 4, pi over 3, that, I went on and on about in chapter 4, if I just remember this special triangle. And the other special triangle helps to memorize, well, what about pi over 3 and what about pi over 6? If I set up that triangle was just a triangle with an adjacent side of 1 and a hypotenuse of 2. The third side, because a squared plus b squared is equal to c squared, the third side of that triangle would be, well, 1 plus b squared equal 4, so b squared equal 3, so b is equal to rad 3. Notice what I get is an opposite side of root 3. And if I look at, say, for example, the sine of theta, that's root 3 over 2. The cosine of theta is 1/2. Notice that this is exactly the same position as 60 degrees or pi over 3, right? Because the cosine of 60 is 1/2, and the sine of 60 is root 3 over 2, same as with the unit circle. And this side up here would give me 30 degrees. So say I wanted to know, well, what's the cosine of 30 degrees? It would be root 3 over 2, whereas the sine of 30 degrees is 1/2. But these are the same measurements as the unit circle, and if I wanted to know the tangent of either angle, it's all here. So this encompasses 2 points on the unit circle in the form of this alternative triangle. And if you just memorize those 2 triangles, that's just a 30, 60, 90 triangle versus a 45, 45, 90 triangle. We can memorize all their base ratios in such a way to remember all of those 3 special positions from the unit circle. Though it doesn't really help us with what about 90 degrees, what about 0 degrees. But anyways, that's it for this video.